In the spring of 1901, sponge divers off the coast of a small Greek island hauled a calcified lump of rock and bronze from the Mediterranean seafloor. It was a seemingly unremarkable piece of debris recovered from an ancient shipwreck overflowing with marble statues and luxury goods. Yet when this heavily corroded mass dried and cracked open at the National Archaeological Museum in Athens, it revealed something utterly impossible for its era. Embedded within the encrusted stone were the distinct, undeniable remains of precision-cut gear wheels. The sheer existence of these interlocking bronze gears presented an immediate and verifiable paradox. The shipwreck was definitively dated to the 1st century BCE, carrying cargo from a century prior, making the artifacts within it over 2,000 years old. At that time in ancient Greece, the known limits of technology revolved around simple pulleys, levers, and rudimentary water clocks. Precision gearing, featuring triangular teeth cut to exact mathematical proportions, was not supposed to appear in the archaeological record for another millennium. This artifact became known as the Antikythera mechanism, named after the island where it was found. It stood as a solitary, magnificent anomaly against the established timeline of human engineering. The device originally consisted of at least 30 separate gears housed within a wooden box, roughly the size of a modern mantel clock. Its front and back faces were adorned with complex dials, pointers, and thousands of tiny, meticulously engraved Greek characters, forming a dense, technical manual wrapped around a mechanical core. For decades, the true nature of this ancient machine eluded researchers. The bronze was so fragile and heavily calcified that any attempt to physically dismantle the lumps would have destroyed the very evidence it contained. Historians and archaeologists debated its purpose fiercely, with early theories ranging from a sophisticated astrolabe to a navigational instrument or perhaps a complex mechanical toy. The lack of comparable artifacts meant that traditional comparative archaeology was entirely useless. The first major breakthrough in deciphering the device relied on the pioneering application of radiography. In the 1970s, science historian Derek de Solla Price and nuclear physicist Charalampos Karakalos subjected the fragments to gamma-ray and X-ray imaging. Their verifiable data pierced the stone casing, mapping the internal structure and revealing a complex train of gears interacting in ways that defied all previous assumptions about antiquity. Price concluded that the device was an astronomical calculator, a mechanical computer designed to predict the positions of celestial bodies. His analysis suggested that the interconnected gears performed mathematical operations mimicking the cycles of the solar system through physical ratios. If a user turned a hand crank on the side of the box, the internal gear trains would drive pointers on the external dials displaying the state of the heavens for any given date in the past or future. To explain the incredible sophistication observed in the radiographs, Price proposed that the mechanism utilized a differential gear. This is a complex mechanical arrangement that allows two shafts to rotate at different speeds, a technology previously thought to have been invented during the Industrial Revolution. While his theory of a differential gear was revolutionary, it sparked intense skepticism among classical historians who argued the evidence was too blurry to support such an advanced claim. The debate over the differential gear highlighted the limitations of two-dimensional X-rays when applied to a crushed, three-dimensional puzzle. The internal gears were superimposed on the radiographic plates, making it nearly impossible to determine exactly which gear engaged with another. The true mechanical architecture remained obscured by the shadows of its own complexity, leaving the full capabilities of the artifact tantalizingly out of reach. The narrative shifted dramatically in 2005 with the formation of the Antikythera Mechanism Research Project. This international coalition of scientists and historians secured access to a massive, custom-built microfocus X-ray computed tomography scanner. Microfocus X-ray computed tomography, or micro-CT, is an advanced imaging technique that uses high-resolution X-rays to create incredibly detailed three-dimensional cross-sections of an object without physically touching it. The data generated by the micro-CT scanner was unprecedented. It allowed researchers to virtually slice through the corroded bronze, isolating individual gears, counting their exact number of teeth and tracing the precise mechanical pathways that had been frozen in place for millennia. The high-resolution scans also revealed thousands of hidden text characters inscribed on the internal plates and the spaces between the gears, effectively uncovering a buried instruction manual written by the ancient engineers. Translating these microscopic inscriptions confirmed the artifact's function beyond any doubt and revealed an astronomical calculator of staggering ambition. The front dial tracked the Greek zodiac and the Egyptian calendar, showing the position of the sun and the moon. The back dials were even more complex, utilizing a spiral display to track the Metonic cycle, a 19-year period central to synchronizing lunar and solar calendars. Perhaps the most astonishing revelation from the decoded text was a smaller subsidiary dial dedicated to tracking the 4-year cycle of the Panhellenic Games, including the ancient Olympics. This proved that the device was not merely an abstract scientific tool, but a machine deeply integrated into the cultural and religious fabric of ancient Greece. It bridged the gap between celestial mechanics and human society. The deeper the scientists looked, the more the mechanical genius of the device astounded them. The micro-CT scans resolved the debate over the differential gear, proving Price wrong but revealing something equally remarkable: an epicyclic gearing system. In this arrangement, one gear revolves around the center of another, a highly sophisticated method for modeling complex, non-circular motions within a confined mechanical space. The ancient creators used this epicyclic gearing to solve a specific astronomical problem known as the lunar anomaly. From Earth, the moon appears to move across the sky at variable speeds, a phenomenon we now know is caused by its elliptical orbit. The mechanism replicated this variable speed using a pin and slot mechanism mounted on 2 overlapping gears, subtly shifting the rotation rate of the lunar pointer to match the actual observable sky. The mathematical precision required to design this pin and slot mechanism in the 2nd century BCE is staggering. It demonstrates a profound understanding of complex astronomical theories, likely those developed by the astronomer Hipparchus, who lived on the island of Rhodes around the time the device was constructed. Hipparchus is renowned for his verifiable work on lunar anomalies, making him a prime suspect in the intellectual lineage of the machine. While Hipparchus provides a theoretical foundation, the physical construction of the calculator points to other potential origins. Some historians argue the mechanical tradition stems from Syracuse, the home of the legendary inventor Archimedes. Historical records from the Roman Republic describe a mechanical planetarium built by Archimedes that was taken to Rome after his death, suggesting a pre-existing tradition of complex astronomical models. Another credible theory suggests the device was built in a specialized workshop on the island of Rhodes, which was a major center for astronomy and engineering during the Hellenistic period. The presence of the Olympic dial, however, complicates this, as its inscriptions use regional month names that point toward Corinth or its colonies, specifically Syracuse in Sicily. The exact workshop remains elusive, veiled by the fragmentary nature of the archaeological record. The enduring puzzle still loomed. If ancient Greece possessed the knowledge and tools to create such an intricate machine, where are the others? The complete absence of any comparable artifacts from the classical world presents a profound challenge to our understanding of technological history. It forces us to confront the severe preservation bias inherent in archaeology, where only a tiny fraction of the past survives to be studied. The rarity of such devices is likely due to the material itself. Bronze was a highly valuable commodity in antiquity. When a complex machine like this broke or became obsolete, it would not have been thrown away. It would have been melted down and recycled into weapons, statues, or coins. The only reason this specific calculator survived is because it sank to the bottom of the sea, protected by the very shipwreck that doomed its owners. This implies that the Antikythera mechanism is not a unique, anomalous invention, but rather the sole survivor of a lost lineage of advanced engineering. The sophistication of its design, featuring prime number gear teeth and standardized components, indicates it was not a prototype. It was the product of a mature technological tradition, honed over generations by master craftsmen whose names, workshops, and intermediate prototypes have been entirely erased from the historical record. The implications of this lost lineage force a radical reassessment of ancient capabilities. It shatters the linear view of technological progress, which assumes a steady upward trajectory from antiquity to the modern era. Instead, it suggests a timeline marked by sudden peaks of brilliance followed by catastrophic losses of knowledge, where sophisticated engineering could vanish for centuries. Following the collapse of the Greco-Roman world, the knowledge required to build such complex geared mechanisms disappeared from Europe. It would take more than a millennium for comparable technology to reappear, emerging in the form of astronomical clocks in medieval European cathedrals during the 14th century. The ancient Greek artifact stands as a silent testament to a thousand-year detour in the history of mechanical engineering. Today, modern horologists and engineers continue to study the high-resolution scans, attempting to build exact physical replicas of the machine. These reconstructions are not merely academic exercises, they are vital tools for testing the mechanical viability of the proposed gear trains. By recreating the device using the tools and materials available in antiquity, researchers verify the practical genius of its original design. Recent studies published by the University College London team have proposed new arrangements for the heavily damaged front dials of the device. By combining the X-ray data with ancient Greek mathematical methods, they have modeled a complex system of concentric rings that would have displayed the movements of all 5 planets known in antiquity. This verifiable research continues to expand the known capabilities of the machine. The lump of calcified bronze hauled from a shipwreck in 1901 has fundamentally rewritten the history of technology. It proves that ancient minds were capable of abstracting the cosmos into mathematics and translating that mathematics into cold, precise bronze. The Antikythera mechanism remains a verifiable marvel, an ancient computer that continues to process the enduring mysteries of human ingenuity.